Okay, so again, so last week we discussed week 3, which is the theoretical, okay? So now we're going to discuss the week 4 mathematical preliminaries. So again, this is for the subject automata and formal language theory. So our course learning outcome for today, or the course learning objective, is by the end of this module, a student is able to, number 1, understand the limits of computability. Number 2, understand different models of computation, including deterministic and non-deterministic models. 3, understand that particular models not only perform computation but are data and can be analyzed and computed. 4, have significant mastery of the techniques of reduction, diagonalization, and induction. 5, demonstrate significant mastery of rigorous mathematical arguments. Okay? So I think from the week 1 and week 2, we already discussed this one. So this is just the definition. So if you remember the sets or the set theory, do you remember, class? So sets are collection of objects in which order of elements and duplication of elements do not matter. So again, this is a collection of objects. Okay? So a sample of the collection of objects or sets as shown on the screen. Okay, we have the 1A, 1, 1, or equals to A, triple A, and 1, and A or 1. So objects in the collection are called the elements of the set. Okay? So example, the collection of persons living in Arnold is a set. So each person living in Arnold is an element of the set. So notation. Sets are usually designated with capital letters, but there are times that, of course, it is in lowercase. Elements of a set are usually designated with lowercase letters. Okay? The roster method of specifying a set consists of surrounding the collection of elements with braces. So actually that is curly brace. So to determine that this is a set, please include the opening curly brace and the closing curly brace. Okay, so don't forget about this one. It encloses the set. It means it belongs to this set. Okay, so don't forget about the braces. And set builder notation has the general form, the variable, or the descriptive statement. So a vertical bar in set builder notation is always read as such that. Okay? When you see a vertical bar or a parallel sign, it means such that. So Venn diagram. This is a sample of the Venn diagram. This is frequently very helpful to depict a set in the abstract as the points inside the circle or any other clue shape. So the Venn diagram are used in mathematics, logic, theological ethics, genetics, study of Hamlet, linguistics, reasoning, and many other areas. Okay, so definition. The set with no element is called the empty set. So actually, empty set or the null set is designated with this symbol, this one. Okay, so two sets A and B are equal if A is a subset of B and B is a subset of A. So if two sets A and B are equal, we write A is equals to B to designate that relationship. Okay? So if two sets A and B are equal, you just have to write it this way. Okay? The set A is a subset of the set B if every element of an A is an element of B. So if A is a subset of B and B contains elements which are not in A, then A is a proper subset of B. So notation subset. Okay? So if A is a subset of B, we write it this way. Okay, you can write it in this way. Designate the relationship. So as you can see, this symbol means is a subset. Okay? So if A is a proper subset of B, we write it this way. So proper subset, you can use this symbol. And if A is not a subset of B, we can write it in this way. So please remember these symbols to designate the relationship. So this one is a subset, this two is a proper subset, and this third one is not a subset. So those are the notations of the subsets. So subset, proper set, and not a subset. So this one, this symbol was given a while ago. It means an empty set or a null set. So don't forget that the symbol for the union is this one. I think we discussed this also in week 1 and week 2. Okay? So to read is equals to x such that x is an, if you see the symbol, which what does it mean? It means what? Element of, right? So such that x is an element of A or x is an element of B. Okay? Next symbol for the intersection. So operations on set for the set theory. This one is the symbol for intersection. So whenever you encounter this symbol, it means intersection. So to read, A is an intersection of B is equals to the X is an such that X is an element of A and X is an element of B. Next operation, we have the difference. Okay, the dash sign or the minus sign. A difference B, so equals X such that X is an element of A and X is not an element of B. So whenever you see this symbol, it means not an element of. This one is an element of. Okay? Next, complement. This one is the symbol for the complement. So if you're going to see this symbol, it means complement. Okay. So if you remember, we discussed the set theory. Okay? So for the intersection of two sets, A and B is the set containing those elements which are elements of A and elements of B. So for example, here on the screen, so we have A here, which contains the set of 3, 4, 6, and 8, while B, we have 1, 2, 3, 5, 6. So what is A intersection of B? So again, intersection, whatever they have the same value. So meaning to say the same value that A and B has is what? 3 and 6. Why 3 and 6? 3 is present in B, okay? And 6 is present in B also. Okay, let's check other numbers. What about 4? From set A. Do we have 4 in set B? No. What about 6? Yes. What about 8? 8 is not present in B. Okay, so the intersection is 3 and 6. Let's check the another set, which is set B. Is 1 present in set A? No. Is 2 present in set A? No. Okay, 3? Yes. What about 5? Is 5 present in A? No. Okay, so again, the right answer is 3 and 6. That is the intersection of the elements. So what about the union? If you remember what is union, we discussed this also. The union of two sets A and B is the set containing those elements which are elements of A or elements of B. So again, the symbol signifies that this is a union, this notation. So if A is equals to 3, 4, 6 and B is equals to 1, 2, 3, 5, 6, then of course we are going to unite. So 1, 2, 3, and then 4, 5, 6. So if you're going to check the elements of A and B, A contains A, B contains, A contains 3, sorry, and B contains 3 also, and A contains 6, and B contains 6. So this is the same element. So since these are same element, you don't have to rewrite it. Just write it once. It's enough. Okay? And of course, arrange it in order. Okay? That's how we got 1, 2, 3, 4, 5, and 6. That is union. So these are the laws. Don't forget about the laws. So A union A is equals to A union B is equals to B union A. So meaning to say it is equal. So A union B union C. So this is equals also. So don't forget about this. So A union B intersection C, we have A union B intersection A union C. It's equals. Okay? So A union B complement is equals to A complement intersection B complement. So it's all the same. So A union empty set is equals to A. It's the same also. So A intersection A is equals to A intersection B, and equals to B intersection A. So these are the laws. Again, A intersection B intersection C is equals to A intersection B and intersection C. So A intersection B union C is equals to A intersection B and union A intersection C. And A intersection B, okay, complement and equals to A complement union B complement, it is equal. And A intersection empty set is equals to empty set. So these are the laws. So union and intersection are commutative operation. So if ever A union B is equals to B union A, and A intersection B is equals to B intersection A. So this one are associative operation. So these are the symbols shown to you earlier as we read from the previous slide. Okay, so these are associative operations. This one is the distributive laws. Okay, so meaning to say, okay, when you say distributive, from here, distribute A, okay, and then distribute this one from A, distribute B, A, distribute to C. That's how we come up to this one. Okay? Next, distributive law. Distribute A to B, distribute A to C. Okay, since the symbol is union, we're going to carry out the operation. Okay, so this is how we come up with A union B intersection A union C through distributive law. A few other elementary properties of intersection and union. So again, don't forget about this law. So when you say A union empty set is equals to A. When you say A intersection empty set, okay, it means empty. And A union A is equals to A, and A intersection A is equals to A. Okay, next is subset and power set. So A is a subset of B if all elements of A are elements of B as well. So again, if you're going to read this one, it means a subset. The power set PA is the set of whose elements are all subsets of A. So when you see this symbol, it means power set. So X such that X is subsets of A. Okay, so learn to read these notations. Okay, proving equality and non-equality. So function establish input-output relationship. We write fx is equals to y for every input there is exactly one output. If fx is equals to y and fx is equals to z, then y is equals to z. We call the set of input for which if f is valid the domain, we call the set of possible output the range. We write domain range. Okay? So next is into and onto. Okay? So a function that maps some input to every one of the elements of the range is said to be onto. Okay? For all y exists x. Okay? So a function is into. Let me highlight this one. A function is into if every element in the domain maps to some element of the range. So this means that fx is defined for every x in the domain. The square root real is not into since square root, okay, negative 3 is not defined. So if not defined, into, if all defined, onto. So relation. An input-output relationship where a single input can have more than one output is called a relation. So if you have a one input and then you have more than output, that is a relation. So because the output is not unique, we write this as less for 3, less for 2, less for 1, less for 0. We can think of this as a set of tuples. So relations as set. An n-ary relation is a set of n tuples. Some relations are infinite. Okay, so we often use infix notation to denote binary. So we can use infix notation, okay, by using this notation. Okay? And an n-ary function is an n plus 1 ary relation. So, binary relation, we have three properties. We have reflexive, we have symmetric, and we have transitive. Okay? So, reflexive, this one is implied by this notation. Symmetric is implied by x dot y implies y dot x. Transitive is implied by x dot y and y dot z implies x dot z. This is called the equivalence relation. So again, don't forget about the three properties. We have the reflexive, we have the symmetric, and we have the transitive. So graphs. Next is the graphs. So graphs have nodes, vertices, and edges. Okay, if you remember the graphs. So directed graph, when the edge have a direction, usually drawn with an arrow, the graph is called the directed graph. So for example, I have a graph. Okay, let me erase this one. I have one here. Okay, example, this is a graph. Assuming this is a graph. So 1, 2, 3, and 4, these are called vertex or vertices. Okay? And the edges are the lines. This one, as of this time, this is undirected graph because there is no direction. If you want this one to be a directed graph, you're going to put an arrow to indicate its direction. So for example, okay, the edge has a direction now. So that is an arrow. So now this is called as the directed graph because the edge have some direction. Okay? So next is the degree, the number of edges attached to a node. In a labeled graph, nodes have in degree and out degree. So when you say degree, normally it's the level of the vertices. Okay? Labeled graphs. When the edge are labeled the graph. For example, let's go back to the graph. For example, this is the graph. I have a directed graph here. And then every edge has a weight or has a label. For example, I'm going to put 5 here. The distance from vertex 1 to vertex 2 is 5. The distance from vertex 2 to 4 is 6. Okay? The distance from vertex 4 to 3 is 7. And then the distance from vertex 3 to 1 is 8. This one is what? A labeled graph or weighted graph. Sometimes this is called as the weighted graph. Okay? Okay, Pats. So, a sequence of nodes connected by edge, a graph is connected if every two nodes are connected by a graph. A path is a cycle if the first and last node in the path are the same. A cycle is simple if only the first and last node are the same. Okay, let's try to apply this path. Okay, let's go back to this graph. Suppose that I'm going to write this one. If I am to write this graph following the direction, it's 1, okay, 2, 4, 3, and 1. This is the path. So I started from the first vertex up to the next vertex following the direction of the edge. Okay? And aside from that, this one is called as a cycle. Why? I started with vertex 1 and I ended with vertex 1. Okay? So that is the cycle. So a cycle is simple if only the first and last node are the same. So next is a tree. A graph is a tree if it's connected and has no simple cycles. The unique node within degree 0 is called the root. So for example, I have a binary tree. Okay, this one is a binary tree here. Okay, so this one is called the root. In degree 0 because this is the root or the topmost. Nodes of degree 1 other than the root are called the leaves. So actually, this is the root. This is the children of the root or the ancestor of this one, lower degree. Okay? These are the leaves, the last nodes. Sometimes this is called as the terminal node. Okay, next. Strings and languages. So strings are defined with respect to an alphabet, which is an arbitrary finite set of symbols. So common alphabets are 0 and 1, binary, and ASCII. So again, ASCII is a value of that is equivalent from the keyboard. Okay, for example, enter, the ASCII value of enter in the keyboard is ASCII 13. But any finite set can be an alphabet. A string over an alphabet is any finite sequence of elements of. So the length of a string is denoted by this one. When you see the symbol, the vertical, and then there's a W here or any alphabet, it means a length of a string. So the set of all strings of length and over summation is denoted by, okay, the summation raised to n. So this is the set of all strings of length. Okay? So more strings. If you're going to see this symbol, if you encounter this symbol, it means what? An empty string. Okay? This symbol is different from this one. This one is an empty string or the epsilon symbol. This one is an element of. Okay? So another notation to use is this one, rather the epsilon. So when you see the symbol, the summation and the star or the asterisk is the set of all strings over the alphabet. When you see the summation symbol, it means what? It means the alphabet. Okay? When you see the symbol summation alphabet plus is okay, the set of all strings with the empty string excluded the set of all strings. So again, be familiar with the notations. So string concatenation, we have some laws. Okay, these are the laws. Okay, u dot, so b dot u, so equals to u, b. Okay, we have the u here. The empty string is equals to u, and then empty string u is equals to u. So the length of u and b is equals to length of u plus length of b. So next, machine language. Only language computers directly understand. Of course, that is the machine language, that is zeros and ones. Natural language of computer. Okay, defined by hardware design. Generally consists of strings of numbers, instruct computers to perform elementary operation, cumbersome for humans. So don't forget about that. When we're talking about language, we're talking about thousands of zeros and ones. Okay? Which is hard to understand for us. But for the computers, that is their language. That is the natural language of a computer that they can understand. Enable for a computer to understand what we type or what we input. For example, we input A, we input B, we press plus, we press enters. The computer will transform the letter A, the letter B, the enter into a machine language before the computer understand our input. Okay? Next, a language is over an alphabet is any subset of this alphabet, which is the set of all strings. Okay, that is any set of strings over an alphabet. So language concatenation. So again, be familiar with the notations. So L means language. Okay. So either you're going to denote it with this one. So if you're going to denote the language with the n power, use LN. Okay. So next is the Kleene Star or the asterisk. If you ever see the symbol asterisk here for the language or L, okay, are empty string and all strings obtained by concatenating a finite number of strings in a language. Okay, so these are the notations as shown on the screen. So this is the language of all even length binary strings, which is the example below. Okay. Next, mathematical statements. So statements are sentences that are true or false. So 1, 0 is equals to 3. AB is a substring of C, B, A. Every square is a rectangle. So again, class, this is just an example statement. So predicates are parameterized statements that are true or false depending on the values of their parameters. So it will vary depending what is the value of x, what is the value of y. Okay? So x is greater than 7 and x is less than 9. So it will vary. X plus y is equals to 5. So it will vary what is the value of x and y. Or x minus y is equals to 5. So again, it will vary depending on the values of x and y. So if x is equals to y, then x is raised to 2 is equals to y raised to 2. So next is logical connectives. So logical connectives produce new statements from simple ones. We have the conjunction, we have the disjunction, we have the implication, we have the negation, we have the logical equivalence. So for the conjunction, okay, sorry, let me erase that. So for the conjunction, kindly use this symbol. For the disjunction, use this symbol. For the implication, use this symbol. Looks like an arrow. And this one is the negation. This one is looks bidirectional arrow. This is the logical equivalence. Okay, so for the conjunction, disjunction, implication, negation, and logical equivalence, so these are the logical connectives. Okay, proving implications. Most theorems are stated in the form of implication. So if A, then B. So to prove it, we assume that A is true and proceed to derive the truth of B by using logical reasoning and known facts. So silly theorem, if 0 is equals to 3, then 5 is equals to 11. So assume 0 is equals to 3, then 0 is equals to 6. Why? Then 5 is equals to 11. So again, these are just an assumption or a theorem that has to be proved depending on the given. Of course, you're going to prove it through logical reasoning. So converse, the converse of the implication AB is the implication BA. It is quite possible that one of these implication is true while the other is false. So 0 is equals to 1, 1 is equals to 1, but 1 is equals to 1, 0 is equals to 1 is true, is false. So contrapositive, the contrapositive of the implication AB is the implication BA. If one of these implication is true, then so is the other. It is often more convenient to prove the contrapositive. So L1, so as you can see here, is equals to L2 star, then L1 is equals to L2. So formatting proofs. So there are rules in formatting the proofs. Okay, there are facts, assertion, and steps. For the facts, things you know include function definition and facts about arithmetic. Assertion, state clearly what you are proving. Steps, list each step. Every step should be justified by a fact. Okay, so those are the rules for formatting. Okay, so again, this is under the week 4, which is mathematical preliminaries. So we are to discuss the Venn diagram using the number 0, 1, 2 until 9. So illustrate the set. So we have two sets here, which is set A and set B. Okay. So now for the set A, we have 4, 7, and 9. For set B, we have 1, 2, 3, 4, and 5. So the solution here to illustrate the sets, we're going to use a Venn diagram. So this is the Venn diagram, the two circles here. So since we have two sets, we have A and B. Okay, it's 1. Now, so 4 is in both sides. So as you can see here, from set A, 4 is present, and from set B, 4 is present. So thus, we're going to put 4 inside the two circles, which are the intersection. Okay? Next, 7 and 9 are only in set A. So meaning to say, 7 and 9 will be placed inside set A. Okay, so that's why it's here. Next, so 1, 2, 3, and 5 are only present in set B. So therefore, 1, 2, 3, and 5 will be placed in this space. Okay, so that's why it is placed here, the 1, 2, 3, and 5, because 1, 2, 3, and 5 is only in set B. Next, so again, we have numbers 0 to 9. So 0, 0, 6, and 8 are not present in A or B. So therefore, there will be placed outside the Venn diagram. Okay, so that's why it is placed here. Okay, so that is a Venn diagram. That's how you use that's how you use to illustrate the sets using the Venn diagram. Okay. So let's try to discuss the intersection members of both set A and B. So again, class, if you remember, the symbol for intersection is this symbol. This one, the color shaded area here, is the A intersection of B. Next, we have the union. When you say union, members of set A or set B or both. Okay? So this is the union of A and B. So again, class, when you say union, the symbol for union is this one. Okay? As shown on the screen below. So next is complementary. When you say complementary, members that not in the set. So this is complementary. Okay? As you can see here. So next is universal set. Okay? So all members. This is the symbol for universal set. This is different from union, ha? Don't forget. So next is subset. So all members of set A are in set B. So this is the subset, okay? So A subset of B. This is the symbol for subset, okay? That's how you illustrate and that's how you use the symbol. So number of elements in a set. So this is the symbol for empty set. Remember this class. The null symbol, okay? So next, okay, once you see the symbol, that's how you're going to present the A union B prime. Okay, that's how you present this or illustrate this using the Venn diagram. So this is the part that is shaded. We have the shaded area. Okay, we have the AB here. So the next is the A prime intersection B prime. Okay. So that's how you're going to present the area, the shaded area. Next, A intersection B prime. Okay. So next is A intersection B prime. So that's how you're going to present the shaded area. So next, we have the A union B prime. So I think these primes and then these symbols are presented last week from the loss or theorem. So if you're just planning to present it or illustrate it using the Venn diagram, you can do it just like this. Okay, we have the A prime union B prime. So that's how you are going to shade the area. So now let's try to do this. We have what is the shaded region. This is just an example. Okay, so the shaded area part here is the B. So it means that B intersection A prime. So next, what is the shaded region? So this is A prime union B. So next, what is this shaded region? How are you going to present this? So this is A union B and then prime. So next, suppose that we have three different sets. We have set A, we have set B, we have set C. So those are the shaded parts. So meaning to say, so B, okay, intersection. So intersection of A union C. Okay, so here's the A set, and then this is the C. So this one is the union, and of course the intersection of those are this one, this part. So next, what is the shaded region? How are you going to present this? So this is the shaded region here is the A union B union C prime. So remember class, how are you going to shade if you are using or going to illustrate using a Venn diagram. So now the shaded region here, A union C union B prime. So that's how you're going to present using a Venn diagram. Okay, sample here, we have different sets. So we have A and we have B. We have set A, we have set B, and we have the datas here. Okay, as you can see, if you are going to check the set A, we have 2, we have 4, we have 6, we have 8, we have 10, we have 12, and we have 14. So that's the element of set A. While on set B, the elements of set B, we have what? We have 2, we have 3, we have 5, we have 7, we have 11, and we have 13. Okay, so U for the universal. So these are natural numbers that are less than 16. So if you are going to check the elements inside the diagram and then inside the rectangle, numbers are less than 16. So let's try to describe set A and set B. What's with set A and what's with set B? So when, if you are to check the set A, the 2, 4, 6, 8, 10, 12, 14 are all even numbers. What about set B? Set B are prime numbers. Okay? Next. So the next example, we have three different sets. We have set A, we have set B, we have set C. So for set A, we have 10, we have 12, 14, we have 16, we have 18, we have 20, we have 24, we have 26, we have 28, we have 22, okay? And we have 30. For set B, we have 12, we have 15, we have 18, we have 24, we have 27, and we have 30. For set C, the elements are, we have 10, we have 15, we have 20, we have 25, and we have 30. So let's try to describe sets U, set A, set B, and set C. So for set U, of course, we have 10, 11, 12, 13, 14, until 30. So that's the universal set. So if you are to check again, set A, all of the numbers here inside the set A are all even numbers. So 10, okay, 20, 30, 12, 18, 24, 14, 26, 28, 16, and 22 are all even numbers. What about set B? So if you are to check set B, okay, it is what? Multiples of 3. Okay? So 12 plus 3, that was 15. 15 plus 3 is 18, plus 3, 21. Okay, plus 3, 24, plus 3, 27, plus 3, 30. Okay? So that's how you're going to describe set B. And then let's try to check what about set C. Set C is multiples of 5. Okay, as you can see here, we have 10, 15, okay, 20, 25, and 30. So that's how you're going to describe universal set, the set A, the set B, and the set C. Okay, so that's the end of the topic for the Venn diagram.